Alright, so we're going to start out the year by talking about atomic theory. We will start out looking at kind of the history of the atom, and then go over the general structure and properties of an atom as well. Before we do that, though, I want to talk about two terms that we're going to see. So these are important that you remember these. This pops up a lot on multiple choice questions. It refers to pure samples and mixtures. So a pure sample, or a pure substance, it's sometimes called, contains particles or units of one specific atom or molecule. So if you have a cup of pure water, that means there's nothing but H2O inside there. That would be a pure sample. However, if you have water, there's H2O in there, but if you put a little bit of salt in there, there's also going to be the Na plus and Cl minus. Even though you can't really see those individual parts, it's a mixture because it contains particles or units of more than one specific atom or molecule. Another example of a pure substance would be like a sheet of iron. If you have something that's solid iron, that's pure Fe, that would be a pure sample. Something like stainless steel, though, which has iron, and then mixed in with the iron is carbon. That would be a mixture. Alright, so mixture isn't always something you can necessarily see. Like if you look at sand, you can see all the individual rocks. That is a mixture, but some mixtures are homogeneous, which means everything looks the same. So there you go, pure samples and mixtures. Alright, here we go with the atomic theory. So let's start off by talking about Democritus. So Democritus was the OG of the atomic theory. He started it all. Believe it or not, back in the 460 range BC, there was a raging debate about the composition of matter. You know, we really didn't know what was going on at all as far as what things were made of, what is fire, what is liquid, what is cold. So they used to sit around and philosophize about what the world is made of. And so one of the debates that was going around was if you took a block of something, okay, let's say we had a block of cheese, and we cut that block of cheese in half. We would have two pieces. Now if we took one of those halves and cut it again, then we could cut it again, and again, and again, and again. You can keep cutting it. Would you ever hit a point where you couldn't cut that cheese any smaller? So most people said no, you would always be able to cut as long as you had a knife sharp enough and a magnifying glass strong enough to see it. You could, in theory, keep cutting forever, never get smaller. Democritus said, nah, he begged to differ. He thought that there would be some point where you would hit an individual piece, something so small that it could not be cut anymore. And it couldn't be cut anymore because it would lose the properties of that substance. He called that thing an atomos, which means uncuttable. And as you may have guessed, that's where we got the word atom from. Okay, so an atom is the smallest part of a particular element that maintains the properties of that element. So we didn't know about elements, we really didn't know about atoms then. This was just a theory of Democritus that things would eventually hit a point where they couldn't be cut anymore. Then there's Lavoisier, looking like a thug there, doing some experiments in his kitchen. So he was a French guy who decided to do some reactions, and what he verified was the law of conservation of mass, which says that mass cannot be created or destroyed. So if you do a reaction, even though things might change form and they look different, the mass overall would stay the same. So the reactions that he would do would be with combustion, with oxygen, and so he found out that if you take fuel and you mix it with air, you end up with a similar mass, or the same mass at the end. So the mass of the air and the mass of your fuel would combine and produce the same mass of products, which would be carbon dioxide and water. So he also discovered oxygen, gave it its name, and discovered the roles that it played in combustion. Lavoisier, though, this was during the French Revolution, and he was a tax collector, so naturally they cut his head off. On to Joseph Proust. So at this point, we had kind of found out about elements. They had started narrowing things down, so we knew about hydrogen, we knew about oxygen, but compounds were something different. Okay, so the law of definite proportions was what was discovered by Joseph Proust, or proposed by Joseph Proust. So prior to Proust, they knew that there was hydrogen and that there was oxygen in water, but what they would have thought was if you had a cup of water, there would be some hydrogens and some oxygens in there, and it was kind of just a random mix, and that's what made up water. So they were all floating around together. But what he did with some analysis was he discovered that water is always 88.8% oxygen and 11.2% hydrogen by mass. So what we realize from this then is that molecules are always in a definite proportion. So that means there's a certain ratio going on there. They didn't really know about compounds. They didn't quite bring it to the H2O thing yet, but they knew that there was a by mass, a percentage, and that was for any compound then. So like if you had something like CH4 methane, they would have found out what the percentage of that was. So it's this percent carbon, this percent hydrogen. Then there's my boy John Dalton, a fellow teacher, who put it all together. So he proposed the idea, actually it was a set of ideas that we call the atomic theory now. So he presumed that if elements were made of tiny indivisible particles, that's what Democritus said, then molecules that have a certain percentage by mass would always be composed of equal numbers of each type of element. Thus, each element in a given compound would account for a consistent percentage of that compound's mass. So water, since it's always 88.8% oxygen and 11.2% hydrogen, he proposed then, since we know the masses of those two, that there would be 2 hydrogens for every 1 oxygen. So John Dalton published a paper in 1808. It was called A System of Chemical Philosophy, and in it were these 4 postulates of the atomic theory. So number 1, each element is composed of tiny particles called atoms. Where did he get that from? Yeah, he jacked it from Democritus. Number 2, all atoms of a given element are identical, and all atoms of different elements are different. So that one was actually his own. And what he's saying there is if you have 2 atoms of iron on separate sides of the world, okay, those 2 atoms of iron, he said, would be identical. Okay, that's what makes it iron, is because they have the same properties. All atoms of different elements are different, so then if you had an atom of, say, sodium, that would obviously be different than the atom of iron. Next, he said that atoms are not created or destroyed in chemical reactions. They are dissociated, combined, or recombined. This is just kind of a rephrasing of what Lavoisier said, the French guy. The idea of the conservation of mass is put in here. So atoms don't disappear and they don't just appear. And then the last one is just an extension of what Proust said. So compounds are formed when atoms of different elements combine with one another. And then a given compound always contains the same relative number of atoms. So then what he was putting together there, then if you have something like water, well, then water is made when 2 H's and 1 O come together, and that would give us H2O. And then that there's always 1 oxygen and 2 hydrogens in water molecules. If it's anything different than that, then it's not water. Also, it's important to note that he was actually wrong in point number 2. So all atoms of a given element are identical. That's not always the case. They're identical in some aspects, the number of protons specifically. However, isotopes, which have a different number of neutrons and will weigh different, are still identical. So one of these irons could have 1 mass and the other iron could have a different mass just because of a different number of neutrons. But both of them have the same number of protons, and as long as they don't have a charge, they'll have the same number of electrons. But number of neutrons can differ between atoms. So then this little Mickey Mouse shape, the classic shape for water, this was something that John Dalton didn't quite understand yet, and something that he didn't propose. This was much later, but he did know that since the mass percent was the same for all of them, and since atoms were composed of indivisible particles, then there must be some kind of structure there where you have 1 oxygen and 2 hydrogens to make up water. And that's just a proposal based upon the law of definite proportions. So I need you guys to understand how revolutionary this idea was. It's something that we're looking at and being like, all right, so what? He figured this out. It was a big deal. Look at the difference in years between Democritus and John Dalton. During all of that time, the idea of an atom even existing was highly debated. Everyone thought that everything was just kind of there. Okay, what actually made it up? The idea of atoms, the idea of this composition, the idea of reactions having the same mass wasn't really understood. No one really cared, to be honest. So this idea coming out was really revolutionary for the time. And in fact, this came out in 1808 when John Dalton published it, but it wasn't really until the 1900s that they even verified that the atom, that scientists came to accept the idea of an atom even existing. It's within our recent history that we've even decided atoms are real. Something that's cool about science is really all about the toys. So the way a lot of discoveries end up being made is someone invents a really cool toy, and then some scientist calls his department head and says, "Hey, look, I saw one of these at this other college. You got to get me one of these so I can play with it." And so that's what J.J. Thomson did. This cathode ray tube, this was a new invention. They were really cool. You put some electrical charge on either side of this device, and what you would get was this green laser beam that shined through this glass tube. That was pretty stinking cool back in the 1800s. So what J.J. Thomson did is he was messing around with it, and he found out that if you put an electric field nearby it, so an electric field has a positive and a negative, just like your batteries do. If you put it near that beam, the beam would actually get attracted to the positive field and repelled by the negative field. So this was pretty cool. And now he could play with this beam, make it bend around, and that stream of particles then had to have something in there. It wasn't just light. It had to be composed of something important. So this idea then that this beam was repelled by a negative charge led to a very important discovery. So he concluded that since that beam of particles was repelled by a negative charge, there had to be something negative in there, and that brought us to the idea of the electron. So he was able to then propose the idea that there was a negatively charged particle called an electron. And all because he was playing with a toy and some magnets. Alright, here's another story about a scientist and some toys. So Ernest Rutherford, right about the time that radiation was first coming out, and he hopped right on that, got himself some radioactive material, did a lot of different experiments using chunks of radioactive items. Talk about another one a little bit later. But in this particular one, took some radioactive material, and then something else that had recently been found to react nicely with radioactive material, which is photo paper. So it's basically a type of paper that when radiation hits it, it kind of glows a little bit. And so they were playing around with this stuff, and he decided, all right, I'm going to take my radioactive material, I'm going to wrap it in a lead block, and drill a hole in that lead block. And what that lets him do is take the radiation and shoot it out in a beam. Okay, he took that beam, and just like Dalton did, Thomson, he shot that beam across a magnetic field, so he's got an electrical charge, the positive and negative, and then what ends up happening is some of the beam would deflect up, and you'd see some blips up there. Some of them shot straight through without missing a beat, and other ones were deflected down. So, that was pretty cool. Here he was shooting this radiation, and he was able to make the radiation change path by putting it next to an electric field, or magnetic field. So the one that is attracted towards the positive and away from the negative, he called a beta particle. The one that went straight through, he called a gamma particle. And the one that went down, he called an alpha particle. So a beta particle is really the same thing as an electron. A gamma particle is just straight up radiation, so there is no mass to it whatsoever. It's energy. And then an alpha particle is protons and neutrons. So it's 2 protons and 2 neutrons. So it has a positive charge, and that's why it was attracted towards the negative. So what that means then is based upon Thomson's discoveries and Rutherford's discoveries, we were able to decide that inside of a nucleus of an atom, or inside of an atom at this point, I didn't know about the nucleus, there is a negatively charged particle, and then there's a positively charged particle. Also, from this experiment, based upon the force at which those particles hit the screen, they were able to figure out that an electron is much smaller than a proton. So a proton is extremely heavy compared to an electron. Also found out in this experiment. So at this point in history, they knew in the atom that there was something positive, that there was something negative. And so they came up with this model of the atom that they called the plum pudding model. And it's like a piece of raisin bread almost. So plum pudding over in England or wherever these people were from is like this bread. See, it's not really a pudding. It's a bread with plums baked into it. A better model for us would be like raisin bread. So if you imagine a piece of bread that has little raisin chunks in it, that's kind of the way they envisioned an atom was. So they envisioned an atom as a big positive mass, so the bread is like this positive region, and then embedded inside of that positive mass is these negatively charged electrons. So this was called the plum pudding model of the atom, and that's the way they kind of envisioned it. So we now know that the atom doesn't look like that, and that what brings us to the quintessential experiment of all chemistry. So here's Ernest Rutherford again in his radiation. So he liked playing with radiation. Once again, he took the lead block with the radioactive material inside. This radioactive material that he used was one that shot out just alpha particles. Alpha particles are very large, they're very heavy, and they're largely positive. So that's why he chose to use them. So what he did, and he didn't actually do this, he was a researcher at this point, so he had a bunch of graduate students who worked underneath him, so he made them do this. He took a piece of gold foil, so gold foil right there. Nice thing about gold foil is it can be pounded extremely thin. It can be pounded to a thickness of almost a few atoms only. And then he surrounded it by photographic paper, so that's that same paper that kind of makes a light blip on it when it gets hit by radiation. And so then what he could do is he could fire protons, or helium nucleuses, alpha particles, through this piece of gold foil and then observe where they hit on this photographic paper. And so what they did was they shot those through, and almost all of them, in fact, 8,000 or 7,999 out of 8,000 would shoot straight through that piece of gold foil, and they would observe a little blip over here on this side. Now, let me set you a picture for this experiment. It's not like they could just kind of kick back with a computer and the computer would count the number of blips for them. This is well before computers. They had to sit in the dark so that they could see the blips. The blips are so tiny because we're talking about alpha particles hitting. They had to set up a microscope. Okay, so they set up a microscope that they were looking through to see those blips. So these graduate students had to sit in the dark, looking through a microscope, staring through a microscope because these spots are so tiny, counting blips. They would do it for days, hours. Ernest Rutherford, he was the man, and so they did whatever he said. So with that plum pudding model of the atom, they figured when they're shooting those alpha particles, they would just fly straight through there. There's not much to stop it. It's just kind of this mass or this region that's positive and negative. And so they just sat down here and they stared and they counted blips. And yeah, all of the blips would go through. Now, what was surprising was Rutherford, for absolutely no reason, no logic whatsoever, told his grad students to take the microscope and move it around to see if any of the blips were happening over on this side. Now, there was absolutely no reason for going and looking over on the other side. They described this experiment as shooting tank shells through a piece of tissue paper. So if you're shooting tank shells through a piece of tissue paper, you're not expecting any of them to come back in the other direction. But once again, they really looked up to this Rutherford fella, and so those graduate students sat back there and they stared for days backwards. What they finally observed changed the course of chemistry history. They found that 1 out of every 8,000 alpha particles that went through, so 7,999 would hit on this side, 1 would hit right back there, so it would bounce back. So these alpha particles were ricocheting off of the gold foil, flying back towards them because they were hitting something. What they hypothesized then is there must be something inside of the atom that those alpha particles would hit and bounce off of. And this was shocking. This was extremely shocking. Think of the tank shell and the tissue paper. Imagine shooting a tank shell at a piece of tissue paper and having it fly back at your face. Yeah, it was like that. Here's what Rutherford proposed then. He said that instead of the atom being this plum pudding model, instead it's composed of 2 regions. It has a negatively charged electron cloud outside of it, so that's what this green region represents. And then in the middle is a very densely packed positive region. And that's what he said was what the electrons or the alpha particles were bouncing off of. So this picture is not drawn to scale at all. The difference in size between the nucleus and the electron cloud is not near that close. It would be like taking a marble and setting it in the middle of a football field. So if we were to draw this to scale, you wouldn't even be able to see the nucleus. And that's why 7,999 of them would shoot straight through, because most of the atom is empty space. So that's one of the things that he proposed. Most of an atom is empty space, and there's a densely packed region in the center that makes up the nucleus. So 1 out of every 8,000 would actually hit the nucleus dead on and bounce back. That's such a small region, it would have to be a very, very targeted shot. But when they move the little microscope around on the outer edges, they would find that sometimes it would just ricochet off. And so they don't all go straight through. Most of them do, but occasionally it would either just ricochet or it would bounce straight back. Okay, this is where the modern atom really started to take shape. This experiment is just an example of someone playing with some toys. So they had this alpha particle generation. They discovered they could pound gold foil into really thin sheets. They had this photographic paper. And so they just kind of put it together and were essentially playing and made this huge discovery. This entire experiment, there's really no reason for it. So the fact that Rutherford set this up for his grad students is just kind of a shot in the dark. It worked out great because we made really amazing discoveries from it, but I mean, it just didn't make any sense. So here's the 2 things that he proposed from his experiment, and these still mostly stand true today. So he said that the nucleus is very, very small and it's positively charged, and at the core it contains the protons and the neutrons. Its negatively charged electrons are extremely tiny and occupy a vast majority of the atom's volume. So they knew the electrons were small, and they knew now that they were on the outside of the atom, and that most of the atom then was just empty space. So from the findings of all of these scientists that we've talked about, here's what they've come up to date. This is about as small as we're going to get within the atom. These are the subatomic particles. So originally Dalton and even Democritus said that there was just an atom, nothing smaller than that. You couldn't divide it any smaller. We've kind of taken it a little bit farther and said, well, you can get smaller than an atom, but it becomes different particles. So once you get smaller than an atom, it's no longer an iron atom or a sulfur atom. It becomes these individual subatomic particles. So a proton is a positively charged. It has a charge of +1. Its mass is relative atomic mass unit of 1. The electron just has an opposite charge of the proton. We've called it negative. And its mass is 0.0005. So that means it's significantly smaller than both the proton and the neutron. We can see it from there. And then the neutron, which has no charge and a mass of 1. Those would be the 3 particles that make up an atom. There's things that go smaller than that, but nothing that we're going to get to in this class.